So let's go here, share. There you go. Okay. Now, so we've learned how to design columns. We've learned how to design base plates. So I guess now it's time to apply this to our project. Okay. So now the only thing that we haven't learned is this third thing here. Okay. So we're going to design the interior columns. We're going to design the base plates for the columns. And then of course, the web crippling and yielding. This is something that I'm going to teach you in this lab, but it's not going to be part of the course requirement, but it's more for your general information. And you'll see by the picture I gave you what we mean by web crippling or yielding. Okay. Now, if you remember, these are the results. Let me go. Now, these are the results. Oh, sorry, I want to annotate. Okay. So basically, I wanted these. I have a column here. I've got a column here. I've got a column here. I've got a column here. And these are the exterior columns. So this is not part of, this is going to be designed next week. These are exterior columns. So here are my interior columns. And whenever you're designing interior columns, in order for you to make sure that you don't have an Rx and an Ry value that are different, you tend to always use square HSSs, okay? Because this way the Rx value is equal to the Ry value, and therefore we always tend to use square HSSs for interior columns. So basically, this is the result of the analysis from ADA, okay? This was the minimum value. So I come across here, I have 507.33 kilonewtons. So I can, like if I want, I can design these two for one size and these two for another size, but I'm not going to bother. I'm just going to design them all for at least 507.33 kilonewtons. So that's what ADA does. It gives me right away what the CF value is for each column. And if you remember, we put these reaction areas here, what they represented is where the columns are going to be sitting underneath the beam. Okay, so that's what these are. Okay, now I've got my CF value from ADA. What I need to know is what is the height of the column. Well, we know our building is 6 meters high, right, or 6,000 millimeters. Now you can do two things. You can either use so there you go. So that's the CF value. So that, I don't have to calculate my dead load, my live load, my tributary area. ADA did all that for me in one shot. And the fact that I went to look at my envelope, I got for all the interior columns, I got the highest value, and that's going to be the CF value. Now, what you can do, you can remove and you know that here, your beam, or I should call it the girder. The girder is going right across here like this, right? And you know that this girder here is 610 millimeters by whatever. I think it was 92 or whatever. Anyways, so and in this case, we know that the columns are sitting underneath. And then here, this is the floor. So if you want, we know that from the top of steel, we got 6,000. Okay. And therefore, if we want, we can actually remove the height of the beam of 610. And therefore, we will get the length of the column equal to 5,390 millimeters. And it could even be lower depending on the sloping that you have to create on your roof. But this would be the guaranteed maximum height of your column. Okay. So does everybody see that? The fact that on the drawing, when we show the column going like this and we show that the beam is going over it, that means that the column is below the beam. When we draw this like this, that means that the column is going to be at the same height of the beam, and the beam is going to be attached to the side. So that's what the difference when you show this on your drawing and you show this on your drawing. Okay. So from ADA, oh, sorry, clear all the drawing. Okay, so now I got my CF, I got my, okay, and what I want you to do is, of course, I told you, whenever you're deciding your columns, always use the cheapest one that they're probably going to pass, and therefore, I want you to use a square HSS, and I want you to use the A500 grade C steel. So now you've got all the information, and you should be able to go and size your column for your project, okay? So you go to the tables, you got your CF value, you got your KL value, you know that you're going to use a HSS, a square one A500, and you go size your column. I don't know what size it is. I have a good idea what size it's going to be, but you guys should tell me what it is, okay? So now you've got, does anybody, now take all this information down, because this is what you're going to need to go to that table and get the size of your column. Does anybody have any questions?
Sir, I have a quick
Yeah,
question.
go ahead.
The 600 minus 610 is that's for everyone, right? Doesn't regardless of what beam you have, or
Well, the beam, we like the beams was a 610 by, I don't remember, was it a 610 by 92 and a 610 by,
Yeah, it was.
so it's 610. In other words, the drop in is smaller, but the columns aren't sitting on the drop in. The columns are sitting underneath the girder here, right? So since it's a 610 by, it can be a 92. I don't care if it's a 610 by 92. 610 is a nominal size. So, I mean, it's going to be either slightly bigger or big, who cares? But 610, so therefore I know that I can subtract the depth of the beam. Since the column is going to be sitting underneath the beam, I can, and this will actually be the maximum length of my column. Now I can use 6,000 and go find a value of the column, but if you want to be a little bit more prudent or a little bit more, optimize a little bit more, you know that the maximum length of your column is going to be 5,390. So you have to go to tables. I don't know if the tables gives you values at 5. I don't remember what it is, but I know that you'll get values of 6,000. I don't know what the other, but that's where you'll go get the value. In other words, use a KL value of at least 5,390. Or if you want, use 6,000. It's up to you.
all right, thank you.
Okay. So that's for your column. Now, once you've sized your column, of course, what you need to do after that is size your base plate. Okay. Now, when it comes to the base plate, okay, here, what you're going to do is basically, once you know the size of your column, okay, what I suggest you do is you let the geometry dictate the size of your base plate. Okay, so basically what you should do is once you know the size of your column, then of course use multiples of 10, you understand? Add 70 on this side, add 70 on that side, and that should end up being the size of your base plate. Okay, because sometimes you let the geometry dictate your base plate and not those formulas. And then once I know this, then of course I can go calculate my n value, and then I can go calculate my thickness. So the size of the base plate is, of course, is going to be, now what I like to do, for example, remember I told you about, we're going to go over this again when we're going to be doing connections, but this is where I go get the minimum edge thickness. Okay, when we get into connections. Okay, so this is a table that recommends, for example, if no matter what, whether it's a flange, whether it's a plate, whether it's whatever, okay, this is the table that recommends what is the minimum edge distance that you should keep from the center of your hole, because this is based on the diameter of the hole, to the edge of whatever it is. In this case, is the edge of your base plate. Okay. Now, the reason why you have two columns here is that, believe it or not, okay, some people, when they want to cut steel, they actually shear it off. Okay. In other words, it gets sheared off, and it gets cut with just by under pressure. And when things get sheared off, well, there's a lot of residual stress here, and therefore to compensate for that deformation residual stress, the edge distance when it's sheared off is always bigger than if it's at a rolled cut, saw cut or flame cut edge. So that's why you have two different sizes. And in my case, since I don't know whether the guy's going to shear off the material or if he's going to cut it, to be on the safe side, instead of using these values here, I like to use these values here. So you can see that when you're using a 3/4 inch bolt, which is usually a good size anchor bolt, or 20 millimeters, okay, you should keep at least 32 to 34 millimeters from the edge. I like to keep 35 as a minimum. So I use 35 as a starting point. And of course, if for whatever reason I need to get to bigger anchor bolts, in other words, 7/8 and so on, I will make this even a little bit bigger. But I will always keep at least 35 millimeters as the distance from the hole. And of course, that's in both directions, okay? And that's where you get the information in terms of the minimum edge distance, okay? And we'll go over this again when we're going to be doing the bolted connections, so that And like I said, so this is where I get my edge distance from this table here. And then look at this. When it's over 36 millimeters, you take the diameter, you multiply by 1.75. And guys, put more than less. In other words, don't go less than, if you want, you can leave 40. You can get into the practice of leaving 40. You understand? 40 and 40. So that means that you'll have ample. In other words, you will leave 35 there, 35 between there and where the member is, and so on. So that's what I would, you understand? So that's where I get the value from, and now you don't know where the 35 comes from. So since I don't know, like if I knew that the guy was going to cut it with a saw, if I knew that the guy was going to, or a flame, you know, the flames, the acetylene flame, and okay, the gas, okay, laser and water jet. If I knew, then I can go down to 25. I can go down to 26 and so on. But I really don't care if I overestimate this edge distance. And I like to use 35 in my case. Okay, so that's where I got that value from. So basically, that's why I have 70 here. I have, like, from here to here, I leave 35, and I like to leave at least 35 on the other side. So this way, when I come and put my washer and I come and put my nut and everything else, it won't interfere with the weld that I put all around and so on. Okay. That's what I like to do. So here, what I suggest is that instead of you, like, for example, taking your CF value, dividing it by your, dividing it by the strength of your concrete and so on, and getting an area, I think the geometry will dictate the size of the plate more than that. So here, for example, you take the size of HSS that you determine for your column, and you add 2 times 70, in other words, and that's going to give you the B and the C value for your plate, okay? So round up to the nearest 10 millimeters is what you should do. Now, the area is CF over BR, okay? So here I have this is BR, okay? So I want you to assume your concrete strength is 25 MPa in this case, okay? That's what I want you to assume in your project. You can use a 25 MPa concrete for your foundations. Now, as long as the area here is less than the area that you had here, you know you're going to be okay. You're not a problem. Now, if all of a sudden this area is smaller than this area here, you're going to have to increase the size of your plate, but I don't think that's going to be the case. I think that the geometry is going to dictate the size of the plate and not necessarily the formula CF over BR. Okay, so you should do it this way. And of course, this is the equation to calculate the thickness of the plate. So once you know the value here, remember that the N value is this distance minus the HSS minus the wall thickness, which how you calculate your N. And of course, there's your CF value. And the N is the size of the base plate minus your HSS minus the wall thickness divided by 2. Okay, just like we did in the example. And once you do that, you got all the variables in here to be able to calculate the plate. And remember, you're going to go and decide whether you need 16 millimeters, 20 millimeters, 25 millimeters, and so on. And then, of course, in this case, the B and the C are the same because you're having a square HSS. And of course, the value of phi for the steel is 0.9. So now you got all the information, and you should be able to size your base plate based on all this information. Is everybody okay with this?
Yeah.
Yes, sir.
Okay. Like I said, you guys are gonna, so you should be able to work it because you got all the information. I'm just guiding you through it, okay, to show you that sometimes, and you'll see when we do the exterior base plates, which is completely out of the scope, but I'm going to show you how to do it, and I'm going to get a lot of Excel spreadsheets for you guys to do that. You'll see that I simplify my life. I start with my geometric constraints, and then I fix certain variables, and then I'd be able to, I take the textbook solution to solve for eccentrically loaded plates, and I already start eliminating some of the variables, and I'll explain that next week or the week after when we do the exterior columns and we do the exterior base plates and so on. Okay, so that's it. So you're going to have to do that, and of course, once you size this. Okay, and once you size this and everything is good, well, you're already ready to do one of the details on your steel drawing. One of the details that you can.
Sir,
Yes.
so I'm looking for I forgot which table for the HSS
Well, you have to
that
look.
we look for
You have to
because
look for a square HSS with the ASTM A500 grade C steel. In other words, it's the very last at the very end of that photo of that file I sent you.
Okay.
Okay. So you want me to go back? This is what I want you to use. I want you to use a square HSS, but I want you to use the A500 grade C steel. Okay.
Yeah, I got it. Okay, okay.
Okay. There you go.
That's the PDF where you scan the book.
Yeah, the one exactly, the one that I used this morning to solve for find the lightest HSS. You understand?
Yeah.
And it's in the same section. You understand? It's somewhere there. And like I said, once you've got your lengths and so on, you should be able to find the lightest one and tell me which one you chose. Okay. I'm sure I picked one already. I won't tell you which one I picked, but I want you guys to do it. I can go into my little calculations here, and I know which one I picked for the HSS. So once you tell me yours, I'll let you know if you're in the right ballpark. I'm just looking at my solution here. Yeah, I picked one. So, I mean, I got to do this project also because like, okay, so there you go. Is that clear for everybody? Now, excuse me. So now you're able to size the column, you're able to size the base plate, okay, and then on top of that, you'll be able to specify the columns on your drawing, on your you'll be able to on your drawing, you'll be able to specify the columns, you'll be able to do the detail of your base plate, and so on. And when you do the detail of the base plate, don't forget what you're going to be doing is you're going to be doing this. Okay, you're going to be drawing this to size. Okay, you're going to just show the edge distance like there. Okay, you're going to show this distance, you're going to show that distance, and then you're going to show this distance. Okay, and that's what you're going to do. That's how you detail on your drawing. You show, you understand? You just show the overall size here, and you show the overall, of course, this, and you show the edge distance that you want to keep. And of course, you do not specify the HSS. That you specify it on your drawings. You try to only show the information required on one area of your drawing, because if ever you need to change this and you forget to go change it on the other detail, it's going to consider it to be a mistake. So don't show. You can draw this to the size you have, but you don't put that you have here HSS so much by so much by so much. Draw it to the one that you have on your drawing, but don't specify it. You just because this detail is for the base plate, and of course you have to say, then you're going to put PL is equal to, and you give me the thickness of your plate. Okay, that's what you have to show. PL is an abbreviation for plate thickness, okay, in steel. Okay, so that's it. So that you should have all the information. Like I said, use 25 MPa, okay, and make sure that the area here that you have is greater than the area required. Okay, now the last thing you should check for, okay, because your beam, okay, and of course use an FY of 300 because it's steel plates. Okay, and that's it. So I'll leave it here so you guys can take down the information, but that's basically it. Or you can just take a screenshot, whatever you guys want to do, and come back to it, or you can go look at the video because this is being recorded. Now, one last thing you have to check for, okay, is what we call web crippling or yielding. In other words, is your web going to cripple or is it going to yield under, okay? And this is what we mean by web crippling or yielding, okay? Now, you're not going to be responsible for this on a test, but this is something that you should be concerned about. This is what you have. Can everybody see what's happening? Okay. Because the forces are going down here, this is similar to the, the bearing resistance for the wood. We want to make sure that BR is good enough. Well, here, you want to make sure that the web that you have here for your beam, okay, you want to make sure that the web that you have here for your beam, when the load goes through this, you want to make sure that this thing doesn't start crushing, okay? So in other words, it can either crimple, in other words, it can just crush because it's too thin, or the steel can actually yield, and therefore it's going to start deforming under the fact that you're going over Fy, okay? So those are the two possibilities, and this is what, and then all of a sudden the thing starts sagging down, and it can get to the point that even it can actually deform to the point where it can collapse, okay? So now, what you have to do is you have to see, is this web thick enough to be able to transfer loads from the beam into the column. And if not, then you need to stiffen the beam. Okay, you need to put stiffeners, okay, on each side, just like we did like on wood, where we would block, you know, we would have the rim beam, or we'd have the blocking to transfer the load through that engineering joist. Well, here we would use steel stiffeners if it's not stiff enough. Now, I can tell you right now, guys, 99% of the people in the industry, they don't even bother calculating this. They just put the stiffeners right away. They figure whether we need them or not, I'm not going to break my head. I'm just going to put them in. And this way I know it's stiffened. So that's what they do. And I consider that to be bad practice. I mean, it's a waste of material and a waste of time. And of course, now, how do we check this? Well, this is what we do, okay? The factored bearing resistance of the web shall be taken as follows for interior loads. Now, these equations are for interior loads, and since these columns are all interior loads, I just gave you one here. You can also have one for exterior loads, but that's only when the column is sitting on top of the beam for exterior loads, and that's very rarely we do that. Okay, for exterior loads, for example, like when we get to the exterior of the building, okay, very rarely do we put the column underneath the beam. Okay, on exterior loads, this is the column, and the beam is always attached on the side of the column, very rarely. Okay, so this is the typical detail of the beam being attached to the column. So that, therefore, in this case, there's no web crippling because the forces are going through the connection. So we don't have to worry about it. But if you do have the situation, there is another formula in the book that you can go and check this. But like I said, very rarely do we support beams on top of columns for exterior loads. For exterior columns, it's always on the side. So I'm only going to give you the interior ones. So basically, this is when the steel will actually yield. In other words, it will yield, and therefore there's one equation when the steel yields, okay? A stocky beam yielding will occur. In other words, you'll surpass Fy, and therefore it would start yielding, and therefore it will deform under the fact that now you're in the plastic range of the steel, and it will start shrinking down. Or the web itself is so thin it will start crimpling, okay? And here's the other equation. So when it crimples, in other words, it's just like a thin sheet of paper. It's too thin and it starts to crimple, and that's what the steel is going to do, is going to start crimpling, and therefore it's going to start deforming. So you got to check both. You got to see whether it's this one or this one that governs. Of course, it's always a smaller one, the lesser of the two, that's going to govern. Now, these are, of course, these are reduction factors, okay? BI, you get this straight out of the handbook, and I'll give you the value. W, of course, you know what W is. W always represents the thickness of the web, okay? Okay, so here, and then, so BI in this case is 0.8, not 0.9, okay? And you'll see that, okay, W is the web thickness, N is the length of bearing, okay? So this means that, okay, so the length of bearing goes from there to there. That is your N value, okay? That's N, okay? Now, people say, well, what's the N value going to be? Well, what you normally do, and I'll show you, we will calculate the N value, okay, from what we're doing. So N is the length of bearing. T is the thickness of the flange, okay? So these, like I said, these variables do not change in steel. When I talk about a small w, I'm always talking about the thickness of the web. When I'm talking a small t, I'm always talking about the thickness of the flange. You understand? So these don't change. And, oh, sorry. Fy, of course, is the yield strength of the steel. In this case, is the steel of your beam, okay? And of course, E is 200,000 MPa is the assumed value that we use for structural steel. So those are all your variables, okay? And like I said, all they're doing here is they're taking the bearing and then they multiply by 10 times the thickness of the flange, because they're able to go out a little bit further to get a bigger area in here. That's all they're doing. Now, what you're going to do is you're going to do this calculation yourself. Oops, I should yield, okay? So here's my HSS, okay? Here's my HSS. And like I said, you leave your 70 millimeters, like the edge distance again, because what's going to happen is that you still have to bolt this, okay? you are still going to have to, like, for example, here's my, they call this a cap plate. It's very similar to a base plate, but it's a cap plate that's on top, right? And of course, it doesn't have to be any wider than your beam. Okay, so in other words, the beam is coming here like this. Okay, here's my beam here, like this. Here's my cap plate, and here's my HSS. So basically, what's happening is that here's the size of my column. Okay, once you determine your HSS, you're going to take that value, you're going to calculate your N value. Okay, and this becomes, in other words, you take your HSS, it's going to be basically be the size of your plate. That's what your N value is going to be, because whatever you get for your base plate here, right, because that's going to be based on your HSS, it's the same edge distance. So therefore, that becomes your N value. That's how you calculate your N value. Now, so here's the first equation. And there's the here, and of course, you're going to take the W. You're going to go find a W for the 610 by 92, because that's the size of the beam that we're using in our project. You're going to go find a W for that beam. Then, of course, you're going to take the size of your column. You're going to add 140 to it. That's going to be your N. And if you want, you should round it up to a multiple of 10, make it even bigger, because you should use multiples of 10. That's what you should be specifying. And of course, T is the thickness of the flange for your 610 by 92, because that's the size of the beam that we're using underneath that column. And of course, here we're using American steel, so our Fy value is 350 MPa. And of course, here's the equation for, okay, one equation, and then 200. Okay, now, if Br is greater than Cf, no stiffeners are required. Okay, so you calculate this equation, and you calculate this equation, and if all of a sudden this Br value is greater than your Cf value, you don't have to put stiffeners. And that's all you have to decide. Now, there's a very good chance that you might not need stiffeners. I don't know. I haven't done this calculation, but you guys are going to tell me, okay? So this is what you have to do. So if Br is greater than Cf, no stiffeners are required. That means that the web itself is stocky enough and it won't crimple. It's thick enough so that it won't crimple, and therefore it will allow the load from the beam to get transferred to the column properly without anything happening to the web itself. Does anybody have any questions?
Yes, sir. I have a question.
Go ahead.
But this is about the column. I'm like not here.
Okay.
Here I understand this part. I mean, if you're done, I can. I
No,
don't need to go back.
no, but ask me your question. Go ahead.
So I just want to say I got a 127 by 127 HSS.
I don't know. You tell me if it's good. I'll let you know once you hand in your project.
Oh my! I mean, I'm
you know
telling you,
what I
it's
mean?
good.
You know what I mean? Like, if you're telling me it's good, it's good. I'm just, you know, like, I don't know. So
No, but the thing is, I just want to make sure something. The KL it was given to us as 5,390. So in the table, there's
in the table, what do you
so in
have
the
as a
table
KL value? What do you have in the table?
there's 5,200 or 5,600. So I
So
chose the 600.
yeah,
Obviously.
you have to choose a 600. You can't go less then. You understand? So based on the KL of 5,600, you got your CF value, you found a CR value. You checked to see which one was the lightest.
I checked. I mean, this is the only one I could have found.
Anyway, so if that's what you're going to live with, Omar, that's what you're going to be putting in your calculations. That's what you're going to be putting in your drawing. Then once it gets submitted, I'll let you know if it's right or wrong. You understand?
No, but tell me, like, is it around the right thing or?
Omar, this is this is the reality of doing a project. Okay.
Oh, nice.
There's no textbook answer. You follow what I'm saying? So if that's your choice, you better feel comfortable that you made the right choice.
Okay.
That's how it is in real life, Omar. You understand? Once I've said it's a 127 by 120, what did you say? 127 by 127 by what? 9.5? Is that what you said?
Yeah.
I don't know. All I'm saying, if that's what you live with, if that's what you're going to specify, that's what you're going to live with for the rest of your life. Welcome to the real world. There's no textbook answers. Okay. So All I'm saying is that these are calculations that you're gonna have to do. I'm gonna be checking these, and like this, and this is what you're gonna be specifying in your drawing. Guys, talk it amongst yourselves, see if you get the same answer, and see who's right and see who's wrong. Guys, I don't mind you guys working together, but I will not tell you what the answer is. You understand? I did it for the beans because the beans are very complicated. It's unbraced, but this is stuff that you should be able to calculate. You follow? So, Omar, I'm not saying that you're wrong. I think you're generally, I mean, like, but are you picking the lightest one? I don't know. But I think that if you get 127 by 9.5, like, what did you get as a CR value?
One second, let me find that
I
now.
hope it's at least 507 kilonewtons.
Yeah, I was in the wrong. I'm in the wrong. Never mind. I'm in the what's it called? The Canadian steel. So
Yep. I can tell you that you're in a Canadian steel there, so you're in the wrong section. Yeah, I found the lightest one. I know what the lightest one is, so I'll know what I'll be looking for. But you're in the right ballpark if you're asking me. You understand? You're in the right ballpark, but you're in the wrong section of the table. So now nobody asked me a question that if ever in the event that this is BR is less than CF, how do you design the stiffeners?
aren't they like the base plate? If I'm not sure actually.
Okay, but first of all, you got to remember something. Okay, this is what's happening. Here is my beam. Here's my cap plate. Here's my column. Okay. And basically, what I want to do is I need to stiffen. In other words, I got to put stiffeners here. That means I'm going to be putting plates on each side so that when I look at it in plan view, if I look at it here, like this, okay, what I will see, this is the web here. Okay, here's a flange at the bottom, and this will stiffen and give lateral support to the web so that this thing will be able to stay there and will be able to get supported. So guess what this looks like? This becomes a column that has this shape here. And you need to calculate the resistance of that column based on that shape there. And if that column, in other words, this is your web, this is the stiffener. So for example, what I like to do is, for example, if I have a 9.2 millimeter web, I like to use a 3/8, I like to use a 10 millimeter plate. I like to use the plates about the size of my web. And then after that, I have to be able to calculate if this column here, like this, if the CR of this column is greater than the CF that's going down, then I know that these stiffeners are good enough. You see how you do it? Now, so if the BR value is greater than the CF, whoa, I don't have to do this calculation. But if the BR value is less than the CF, well, I have to provide stiffeners, okay? And that's what you're doing. And what you're doing, you're actually welding this all around here. Okay, this is welded all around. When we get into welding, you'll know what size of weld to specify. That's going to be in your connections. We're going to learn about that. So that gets welded all around, and therefore these two plates get welded to your web, and they form a column. Okay, and therefore this is what you'd have to do if it's required, guys. Okay, so this is what you have to do if it's required. So, oops. So when BR is less than SPF, bearing stiffeners are required. So that you have no choice because your web is not strong enough. Okay, bearing stiffeners shall bear against the flange or flanges through which they receive their loads and shall extend approximately to the edge of the flange plates. or flange angles. They shall be designed as columns according to clause 13.3, and that's that formula, CR is equal to phi A Fy 1 minus lambda to the all, and all that, assuming that the column consists of a pair of stiffeners that are centrally located, okay, on the web, no more than 25 times the thickness of the interior stiffener. So in other words, people say, well, how much of a web do I take? Well, if I use a 10 millimeter plate for stiffeners, I'm allowed to go 250 millimeters away, and I'll show you how to do that. The effective column length, KL, instead of taking 1 here, okay, you can use at least a K value of 0.75, shall not be less than 3/4 of the length of the stiffeners in calculating the value of K. So in other words, the K value here can be 0.75 because you're welding at the top and welding at the bottom, okay? But if you want, you can use 1, it doesn't matter. Only that portion of the stiffeners outside the angle fillet or flange to flange web shall be considered effective. So what they're saying here is this, so that you guys can understand, is that this is my beam. And you guys should realize that there's a fillet. You must have seen this. There's a fillet in here like this, okay? And there's my beam. So I'm going to be putting my stiffener in here. They don't want you to consider this part here to be part of your stiffener. They want you to exclude this part. So that's what they mean. Okay, only that portion of the stiffener outside the angle fillet of the web to web welds shall be considered effective in bearing. Bearing stiffeners shall be connected to the web to develop the full force required to carry the stiffeners into the web and vice versa. So they're saying that this thing has to be welded sufficiently so that all these two things will act together, okay? So that's the definition. And now how to do the calculation? Well, if BR is less than CF, if it is, now, like I said, if it isn't, you don't have to worry about this, but if it is, then, well, here is that inside, you see that K value there? Okay, this is that inside fillet of the flange to the web and all that. So this is the W610 by 92. This is where you get all the geometric properties of this. And of course, what's going to happen is the stiffener, okay, when you put in your stiffener, you're going to be putting it, you're not going to go right up to the edge because you have this little fillet here. You're going to put your stiffener like this, and your stiffener is going to go here like this. Your stiffener is going to go here like this, okay? And of course, that's how your stiffener is going to be. And of course, after that, you're going to be welding these all the way around on both sides, and you're going to connect the two of them together. And what this is going to do, it's going to reinforce the web so that it doesn't yield and it doesn't crimple, and that's what you're doing. So this is all the information that you need, okay, with all in terms of the geometric properties, okay? So a W610 by 92 is a W24 by 62 in imperial. So that's where you get all the information. And if ever you need to do this, so that's where you get all the information. And now, as far as, okay, so BR, okay, so this is what happens. So 610 by 92, web to, okay, so you have B over 2, right? So in other words, that's the distance from here to here, right? Minus K1, okay, minus the little fillet here. That's going to be the web that's effective to stiffen. That's what they were saying. So therefore here I end up getting 50 millimeters. Okay, so I end up getting a 50 millimeter width here for my stiffeners. As far as the height goes, well, the height is D minus 2T, 735. Okay, that's the height. And I'm going to use a 10 millimeter plate. Why? Because I like to use a plate that is equivalent to the web. So here my web is 10.9, so I'm going to use a 10 millimeter plate for my stiffeners. So now I've got the area of my stiffeners on each side. Okay, so that's what they were saying, that you got to keep this area. You don't even include it in your calculation. You just include these two areas. And then once you've worked out your geometry, everything's based on geometry. You can't do anything without your geometry. Then you can go ahead and start calculating the resistance of that quote unquote column that you're creating inside of this beam. So basically, 10 times the thickness of my stiffener. So 25 times, sorry, 25 times, this is 10. So therefore I would take a length here of 250 millimeters. That would be part of my column. And then of course, this is my column and my column, okay? And now of course, what I need to do is I need to calculate the, I need to calculate the weaker. So Ix is equal to IC, and this is where all that good stuff comes back into practice, your parallel axis theorem, where you're going to transform this and calculate your Ix value for this particular cross section. And you know that the Rx value is equal to Ix over A, so I calculate the area of this, okay? If you need to do it, you calculate the area of this. So that gives you the Rx value, because you know, like in terms of Y, this is much stronger because of this height here. So therefore, this is the one that's going to govern. But if you're not sure, you should do both. And of course, in this case, the Ix value ends up being this, based on this geometry. And of course, my area, I take the area of that, the area of that, the area of that. And of course, I get my, what is Rx is equal to Ix divided by 8, take the square root. So I have the Rx value. Now, I know that the BE over T should be less than or equal to 500 for flanges, okay? So therefore, I check that to make sure it's okay. I'm okay. Now I take my KL over R. Like they said, you can use 75% of your length. My length is this, my Rx. So therefore, I get my KL over Rx value. And of course, I go to table. Since I want to use table 4.4, I've got my, okay. I go to table here based on 16. And of course, my Fy equal to 300 because I'm using, oh no, yeah, I'm using 300. So therefore, I can get the value of CR over A. And I get 307. I know my A value. There's my CR value way over 7. And therefore, my stiffeners are good. And that's how you would do it if you'd ever have to add stiffeners, guys. Okay. Now, I don't like the calculation. I did it for you to show you how it gets done. And like I said, this will never be on a test. I don't expect any, but this is to show you, like when you go up and you start reading something in the code, like this is what you do. You come here and it says, when BR is less than BF, then this is what you read. Bearing stiffeners shall bear against the flange to flange throughout which they receive their load and shall extend approximately to the edge of the flange plate. The reason why they say approximately, because everybody knows that when you're looking at, okay, like the reason to the edge of the flange plates, because there's always a little fillet there, okay? And therefore you can't bring it, you cannot go all the way to the edge because the fillet is there. So they say to the edge of the flange plate. That's what they're talking about, to compensate for this little fillet that's around here at the end of the flange, okay? And shall be designed as columns, and that's where that formula comes in, okay? And of course, I did it with the table, because I made sure I was able to use table 4.4. Assuming that the column section consists of a pair of stiffeners and are centrally located about the web, not more than 25 times the thickness of the interior stiffeners. And that's, like in other words, I decided to use 10 millimeters, so I was able to go to a length of 250. And the effective length of the column KL shall not be less than 3/4. In other words, take your K value equal to 0.75. That's what they're saying, 3/4 of the ratio KL over R, and that's what I did. And therefore, now I got my KL over R. I check to make sure that I can use table 4.4. I get my CR over A value. I know what my A value is because I have the area of my column, and I get my CR value greater than my CF value. I'm okay. And only that portion of the stiffness outside the fillet, okay, of the flange to web shall be considered effective in bearing, okay? So they don't want you to consider this part here to be effective in bearing, okay? And therefore, that's what I did. I calculated that distance there. And bearing stiffeners shall be connected to the web to fully develop the required carrying capacity. And that means that they want you to make sure that you weld this properly. And when we get into welds, I'll teach you what size of weld you would actually specify there, okay? Most likely it would be like, anyway, 8 millimeter or no less than a 6 millimeter, and at most an 8 millimeter weld, okay? And that's it. So now you guys have a good inkling of what's required when we're talking about bearing stiffeners. And like I said, 99 times of the case, guys, Most people don't even do this calculation. They just put stiffeners in, they weld them, and they figure better safe than sorry, and they go ahead and just put stiffeners all over the place. Okay. And like I said, all the information is there. And like I said, that was my column. And this, this is where all this good stuff comes into practice. How do I calculate the moment of inertia of this cross section? How do I calculate the Rx of this section? Well, simply take the moment of inertia divided by A. And you can appreciate that, when you take the IC, the base times the height, this height here of 250 is going to be it's going to be much greater than the IC of this one. So that's why I only bother calculating it with respect to one. In other words, I calculated with respect to the weaker one, which was this one here in this case. Okay. In other words, if you're not sure, you should do both and take the smaller of you should calculate, like in other words, I calculated here. I calculated the moment of inertia with this because this is the base. I mean, this is the height, and you know that it's 1/12 the base times the height cubed. So this is the height here, and then this here, of course. And if you look at this height here, you can see that this is the height that you have in this direction, and therefore this is going to give you a bigger moment of inertia than that one. But if you're not sure, you should calculate both if you're not sure. And then after that, once you've calculated that, you know that the radius of gyration is the moment of inertia divided by the area. And now I got my R value, and now I got my IX value, my A value. I can calculate my R value, and of course now I can make sure I can use table 4.4. Yeah, I check. I can use table 4.4. Okay. And in this case, I'm going to go ahead and all of a sudden, and here it says it. Okay, for plate girder stiffeners, that's the requirement you have to meet. It says it right here. So this is a plate girder stiffener. Okay. And therefore this is it, and therefore I go and get the value of CR because I know what my A value is. Otherwise, I would just I could do the same thing. I can use the equation. I can use the equation CR is equal to phi A Fy 1 minus lambda to the, I forgot what it was, to the 1 minus n over 1, oh, sorry, 1 over n. Anyways, I can use that equation. I would get the same answer. I can, if I want to. Okay. It's up to you. And that's it. So, like I said, you're going to check it. And if all of a sudden you do need bearing stiffeners, then don't bother calculating it. I've already calculated for you. All you're going to do is put 2 stiffeners, 3/8 of an inch, 10 millimeters thick on each side. And that's what you're going to do. So the bearing stiffeners have been calculated for you, but you have to determine whether or not it's required. And I think, if I'm not mistaken, what's this? Oh, the end.
Sir,
yes.
Can we go back to the first slide and the second one, please? Sorry.
The first one and the second one. Sure. The very first one and the second one. Let me go back here.
No. Like, wait.
You never thought that this was possible in steel, right?
No, I've seen it actually. So
I'm glad. That's a sad thing to see when that happens. I know. Okay, so let's go back to the first slide and the second slide. This one here. This one you're talking about?
Yeah.
Okay.
Yeah, just making sure. Yeah, I think we're good. Yeah, I found my mistake. Sorry about that.
And what did you get as a column size?
I got 178 by 178. HSS.
That doesn't tell me anything because 178 by 178, I have 6.4.
I know.
I can have an 8. I can have a 9.5.
It's 6.4.
I think you're hitting the right. You're right in the ballpark. Okay.
Okay, good.
Okay, sounds good. Okay, and guys, let me just anything else on this? Like I said, this is being taped. You'll get the video. So, guys, that's it for the lab. I hope you have a better.
I also have a question about the You remember the slopes we did on the roof last week? Like you explained it.
Yeah. Okay, hold on. Okay,
I just want to make sure something.
Okay, but hold on. Can I stop sharing this, guys? Any more questions on this lab before I stop sharing?
I just have a question.
Yeah, go ahead, Adriano.
Your CF, because I'm trying to do it right now, but your CF is your factor load times your tributary area, right?
No, my CF for this, I get it straight from ADA.
Okay.
And Adriano, the reason why you cannot do that, okay, because look, I'm glad you brought this up, but look, I can tell you, is that you see what happens is that in this case, like this is my column here, that's my column there, right? That's my column there, that's my column there. That's my column there, that's my column there. Let's just say that this was the situation, you understand? And I had a column in here, I had a column in here, I had a column in here. You understand? Now, if all my beams were simply supported like this, do you follow? When all my beams are simply supported like this, right? You see what I'm drawing, Adriano?
Yeah. Yeah.
Okay. Then I can go and calculate AF. But is
Okay.
that what I have for the Gerber system?
No, because it passes over it. Over the column.
Exactly. And that's going to affect, you understand? And that's going to affect how the CF is going to go into the column.
Okay.
So keep in mind, like I said, this way of calculating tributary areas is only valid for things that are connected simply supported. Okay? Because guys, the real definition of the tributary area is from point of zero shear to your supporting member. Now, the reason why this works for simply supported, because the point of zero shear in a simply supported member is right in the middle. So for those, but the real definition of tributary area is, so if I can find the point of zero shear, Adriano, for the Gerber system, I can go and calculate the tributary area. But what do you want to do with that? ADA gives you the results right away.
Yeah, I have to go look back now.
Well, I gave it a value, 507.3. I went to get these from ADA.
Oh, okay. So
This is
I
you don't,
thought that's design.
all I'm saying is, I hope, did I use the right ones, guys? Did anybody check to make
Yeah,
sure?
you did. I did.
And
It
it was
was correct.
500, like, and I think that this is with the this is the CF with the right beam sizes, right?
Yes, exactly. 92.
Exactly. In other
90.
words, this is the analysis I ran after I put in the 610 by 92 and all the right beam sizes. So your CF value is, and as a
Okay,
matter
so
of
this
fact,
is the results. This
sorry,
is the results from your girders, right?
I'm sorry,
Yeah.
can you repeat that?
Yeah, the results that we see on the screen from ADA is your results from the Gerber girders.
Yeah, exactly. That's what it is.
Okay.
Because
Yeah, I just have to go make sure I have the.
that's where the interior column is just supporting the Gerber girder.
Yeah, exactly.
Okay. Okay. So that's where those columns are, and those reaction areas are. That's where the columns are sitting. You understand?
Okay. Yeah.
And if I'm not mistaken, like if you remember way back when, I believe that when you put, I think it's a load case where you put 100% here, 100% here, and 50% all the way along. That gives you the highest. I'm trying to remember which load. It even tells you which load case is going to give you the highest value, but you don't have to worry about that. You just go to your envelope and you get your values. So like I said, now if you want to become really, fine tuned, you can make these two columns one size, and then because this is only 445, you can make these a different size if you want. But let's not worry about that, because you might
Yeah,
end up.
because they're like, yeah,
You follow what
saving
I'm
some
saying?
money.
You can save some money. You know what I'm saying? But here, like I said, when it comes to column, guys, then the other thing about steel, guys, you got to keep in mind that there might be a little bit of savings when you specify, but because you're not repeating it over and over again, that saving might not be there. Because in steel, what really is economical if you can repeat. You understand? So when the guy buys his HSSs, he buys them all one. Because if he buys his HSS for this size here, and all of a sudden he has to scrap 10% of it, what savings do you have? You follow? So anyways, like it's just a question of, like I said, but if you want, you can design for these columns here because they are a lower. I would take this one here, okay, and I would, if you want. But
Okay.
let's keep our life simple. We'll size one and we'll make them the same all the way across. Is that okay with
Okay.
everybody?
Yeah. So if we finish with the columns, can we go to the roof? I just wanna.
Yeah. Well, before we move on, I want to make sure that we're all on the same page. If anybody else has any question before I stop sharing this.
And for the last thing you showed us here on these slides, we might have it or we might not. Like we have to check when we do the
You have to
calculation.
check. You have to check. You have to calculate both BR values, right, based on what I show you there. And if the BR value is greater than the CF, you don't have to do that. If they do,
And,
well, you don't have to calculate because I did it for you. You know.
and okay. And all these calculation you want to see on the
Oh, I
project.
want to I want to see the BR and show me if the BR is greater than the CF. You understand?
Okay.
And then if it isn't, of course, you just take the slides and you show me the calculations in your design brief. Okay?
Okay.
Because I knew that if I would leave it up to you guys would be totally lost to calculate those bearings, you know. But now you got an idea of how. So that's where all this stuff can, you know. Okay, so I'm going to stop sharing this. So you want to ask something about the roof? Hold on a second. So if there's no more questions on this, I'm going to close this, stop sharing this. And Omar, I'm going to take out the white screen, and first of all, I'll let you guys be able to participate. I'm going to take the white screen so you can show me on the white screen what you want to do. Okay, so draw me what you asked me to do, Omar.
No, I can share what I wanna make sure of. I can share the screen of, or
Okay,
if you can,
okay,
if you,
share me your screen. It's even better. Hold on a second. I'm going to stop sharing. Share me your screen. This way, well, yeah, it'll be even easier. Go ahead.
just one single set. Let me find the.
Omar, we got lots of time. It's only 11 o'clock. It's just that it makes the recording longer, so people who want to look at the recording, they're going to say, here Omar's var saying, let me find what I'm looking for.
Okay, I found it. That
You
wasn't
found.
hard.
Go ahead.
So, here we go. So can you see my screen?
Yeah. Can I just hold on a second? Can you give me permission to request so that I can point at things?
Yeah, approve.
You approved. Oh, thank you, Omar. Appreciate it.
No problem. So, so I just want to make sure of something because I calculated them. You see the here the what's it called?
The elevations. Okay.
Yeah, the elevation. So what I did is it was around 0. 1 second. Let me tell you. Yeah. So the deepest one I got is 360 meters. So I put it to like 400 millimeters, basically. So that, like, you know what I mean?
Okay, I understand what you're saying. Hold on. Okay. Can I annotate on your thing?
Yeah, yeah.
Where's the annotation?
Well, I think you have to find it from your.
I've got it. I got it. Okay. So basically, are you putting your drains where these ones are, the same place?
Yeah. Yeah. Exactly. Same place.
Okay. So we'll keep them at the same place. So this way, okay. So basically, here we have 10 meters, 10 meters, right?
Yeah.
10 meters. Okay. Here we have 9 meters, 9 meters. Is that right? 9 meters. Am I correct? Let me take out the project. I have it.
Yeah, it was 9 meters. Yeah, it was 9 meters.
Well, I don't have to. Okay, so it's 9 meters and that's 10 meters. Okay. So in other words, what we're saying is that from here to here, okay, we have 20 meters, right? And from here to here, I have 18 meters, right?
Exactly.
So what's 20,000 times 0.02? That's 400. Okay.
Yeah.
And then we want to put the shoe of the joist on top of that, so another 100. So yeah, therefore here we're going to drop 500.
That's what I did exactly.
So here is minus 500, Omar. Okay. Now, if this is minus 500, right, what would this one be?
300.
No, 250. It's exactly halfway.
I mean, I put. Oh, okay. So you don't.
You understand? In other words, what like between here and here, what would this one be? So you have to. You understand what I'm saying, right? Now, this one here can be slightly different because I believe that this is only 18, right? In other words, this is 18, and in this direction it's only 10. So what's 1800? 18,000 divided. This would be 360, right?
Yeah.
360 plus 100. So in other words, this one would be at 460 instead of 500. So you know you can make it a little bit less. But if you want, make it at 500, as long as you have
Yeah.
2%. Okay.
I
And there you go.
see.
And then after that, mathematically, you calculate what the other values are.
So they don't have to be the same, like from one side to the other. So I can do one side.
Oh yeah. Like as long as you maintain 2%, that's the minimum. You
Mm.
understand? So in other words, here you could put 500. And here we said this was 500 because we had the 10 millimeters, 100 millimeters for the shoe. And here we said 360, right? Plus, so here it would be 460. How's that? Right?
That's
Now,
a choice, right? I can just keep them the same.
or if you want, you could keep them the same.
Okay.
It's up to you. Understand? But all I'm saying that they will both. But then, if you make, like, in other words, just keep in mind that here you have to, like I said, this one, like this will be, if you make this one 460, remember that this is 230 over here. It's exactly halfway between those two to maintain. You understand? You have to keep the same. You know what I mean?
Yeah, I see what you're saying. But probably I'm gonna keep the same. I just don't wanna.
What would be the value here?
At the end, it would be 100, right?
Yeah.
Oh wait.
Yeah.
Yeah.
Yeah, exactly. You always want to drop by at least 100. So here you like see this. Whoever did this drawing, I penalized her by not putting minus 100 here. You understand?
Yep.
Okay.
Okay. Just making sure. All right. Cool.
Okay, because in other words, because you want to make sure that the joist here, okay, sits on top of the beam, and this whole steel has to be dropped by 100. Okay.
All right. Thank you, sir.
Sounds good. Well, that's it. So you're on the right track, Omar. Anyways, so I'm glad you asked the question because I'm pretty sure a lot of people would have the same question, but they're not there yet. You understand? So can I stop recording so it won't be too long? I'll put on pause.